Hello guys, my name is Tu. In this video, I'll be showing you on how do we do a correlation of simulation for a model with a complicated geometry such as grill to its equivalent simplified model. For example, the model on the left, we have grill features throughout its model, and this model on the right side is just to remove all the tiny holes and get the equivalent area basic shapes. So if you are trying to do a simulation on this structure, definitely we will need more time, we need to spend more time to do the meshing, because probably you will not get a very nice mesh because there are so many tiny features, and you need to divide the mesh into tiny smaller geometries in order to mesh them into a better shapes. So, and if you are doing the meshing for this simplified model, is actually very simple. So how the question comes, where is there a way we can simplify this geometry by using the simplified model? So now let me show you about this in this video. So by using NX software, we can directly go to the pre-post for simulation environment and directly create the files to do the work. So we'll be working with a linear static simulation because we're just trying to demonstrate the linear correlation by using a linear static. So now let's try to do a 2D mesh and select this geometry. I'll be using a size of 2 and click OK. Notice the time required to do the meshing and process the mesh. So now the mesh has been done. This the mesh actually looks quite good, except for this area where the mesh is slightly larger compared to the rest of the mesh size. So yeah, so if you need to simplify this geometry, produce a better mesh, you need to simplify this geometry into divide it into multiple smaller regions in order to mesh them evenly. Now let's try to do the mesh for this right model, which is a simplified version, and you can see that within a split second the mesh has been done. So this is the benefits of having a simplified model. Now we need to assign the material for this two mesh. The first mesh is located within the thin shell number 1. The second mesh is located in thin shell number 2. So for thin shell number 1, we'll change the property to assign it to a material which is a local material called the steel material. And we'll just put the default thickness as 1 millimeters. And OK. For the second model, second mesh, we'll just need to do the same thing, just that I'll need to duplicate the same material. For example, I've choose the steel material previously, and I'll just quickly duplicate it, and I'll just keep a copy of it so that I can modify it later without adjusting onto the first mesh. So this they are having the same property, just that they will have a different material model, and we can adjust the material model later independently. So this mesh here will have the steel material. This mesh here will have the duplicated steel material as well. So now the fan, after completing the mesh and the material, let's move on to define the boundary conditions and the loading conditions. So we'll double click on the sim file. Here we'll need to go to the constraint type and choose the most basic constraint, which is a fixed constraint to fix all the degree of freedoms of the nodes. So I'll just quickly show the top view and choose the polygon edge and choose all the top edges and also the bottom edges. So you need to be careful not to select the tiny circular models, circular shapes. Now the fixed constraint has been done. Let's move on to define the pressure loads. For example, I will be using a component type because I'm not sure about the 2D mesh top and bottom face. Therefore, by using a component methods, it's allowing me to be conveniently defining the magnitude in the standard XYZ direction. I'll be using the polygon face and choose two faces, and for the P, X and Y will be 0, PZ is negative 10 kilopascal. So we can quickly do a visual check on the direction of the arrow to make sure that those arrows are pointing in the same direction. So now that the boundary and the loading has been done, we can proceed to click on the solve button to solve the problem. Click OK and the solving has begun. Now that the solution has been done, and we'll quickly look into the results. So the first one that we'll be looking at is the displacement results. So notice that, let me just quickly hide the mesh. So hide the mesh. Okay, so for the displacement result, definitely there are very significant differences between the two, because even though they are having the same thickness, the one on the left, you have all the grill features. The one on the right side does not have the grill feature, thus we have a stronger stiffness and thus a lesser displacement result. So therefore, the grill feature will have the higher displacement results very significantly. Now let's look into the stress unaveraged results. So we can't do much on the stress result, because stress result for linear static is actually geometry dependent. I repeat myself again, stress result for linear static is geometry dependent. There is no way we can get the equivalent stress result between the two, because the geometry is different, full stop. Unless, but if you look into the general contour plot in the general manner, we can still see that the color is the same. For example, here is the blue color, and here will be blue color. Just that here will be light blue, and here will be light blue. Just that we are unable to avoid the localized stress for each of the feature. For example, the localized stress is in green color, whereas because there is no hole here, therefore we are not getting the localized stress at this location. So that's there are some drawbacks if you are using the simplified model. So, but anyway, I'll just continue here and try to show you for the displacement results. So how do we correlate the simplified model to have a same displacement result on the left side? So now let me quickly jot down the differences between the two. For example, the first model will have the highest peak at 0.182. So I'll just quickly write the value here, 0.182. Okay, I'll just erase this for now. Now let's show the model on the right side. The right side model will have a value of 0.153. So by having this value, we can try to figure out the percentage of decrease of displacement. So I'll just quickly change this to decrease of displacement. So it's equal to this value minus this value divided by this value times 100%. So this is a 15.9% of reduction from the first model to the second model. So let's go back to the simulation model here, and how do we correlate? So because we are not trying to change the pressure loading at all, we are not trying to change the boundary condition at all, so there is only one area that we can change, which is the material properties. And for that reason, we need to go back to the fan file and change and look into the material properties. So I have this material for the highlighted model, and I have this material for this right side model. So I'll need to adjust this material properties, and I'll be adjusting at the Young modulus. For example, I'll try to plot the Young modulus graphs in the new window, and I can quickly plot the magnitude of this value, and I'll write it down in my calculations. So this 0.182 is the actual displacement, and with the actual modulus Young, which is 2.09694 to the power of 8. So at this cell, I'm trying to get the equivalent modulus Young for this simplified model. So that will be equals to the modulus Young reduced by 15.9%. So times with 100 minus this value over 100. So the new value is reduced because we are trying to reduce the modulus Young to get the equivalent displacement result. So we'll just copy this value here and paste it onto here to get for the still copy and adjust. We'll just say equivalent to grill structure. Okay. Now, once we have changed the material property, we can just quickly rerun the simulation, going back to the sim file and press on the solve button and solve it. So that now the solution has been done, let's quickly look into the displacement results. So we can quickly compare the displacement result between the two. We look into each of them separately. So first of all, the model on the left side, we have a 0.182. Model on the right side, we also have the same displacement result, and therefore we are successfully adjust the material property to get the equivalent displacement result between these two models, one with the grill feature and the other without the grill feature. And for the stress result, so again, if you are doing a simplified method, that means we are actually ignoring the localized stress for each of the tiny holes. So this depends on your personal judgment whether this approach is a suitable approach for your application. And therefore, I wrapped up this video, and thank you for watching my video. I hope you enjoyed it. Thank you very much. Bye.